In the last video, we have defined partial correlation using an algorithm. Regress both x and y on the conditioning variables and then find the correlation between the residuals. This algorithm, while not infeasible to be carried out in practice, is nevertheless rarely used because it may be simplified a lot. We shall illustrate this with 5 variables u, w, x and z. Suppose that we want to compute rho xy dot zw or rxy dot zw. That is the partial correlation between x and y given z and w. The first is a theoretical quantity based on the probability distribution, while this is based on data. Note that we are not caring about u here. U does not occur in any of these lists. First, we need to write down the dispersion matrix of only the 4 variables involved. Notice that u is absent. Also notice the order. The conditioning variables, namely z and w, come first. They come first, and the variables of interest x and y, they come last. If we are computing rho, in that case this should be the dispersion matrix based on the probability distribution. If we are computing this empirical quantity, then this should be the sample dispersion matrix. Now we shall partition the matrix accordingly. So you get A, B, B transpose and C. Then the matrix D, which is C minus B transpose A inverse B, is called the partial dispersion matrix of x and y given z and w. This is a 2 by 2 matrix. Treat this as your dispersion matrix and compute correlation based on it. That is, you take the off-diagonal element of it, d12, divided by the square root of the products of the diagonals, d11 and d22. This quantity will be your partial correlation. We introduce the partial dispersion matrix C minus B prime A inverse B. It occurs in various contexts in linear algebra. One such context helps us here. Recall that the original dispersion matrix, after you have dropped all the unnecessary variables and reordered the others, was this A, B, B prime, C. Now suppose we start applying Gauss-Jordan elimination to this matrix. But we stop the moment A turns into the identity matrix. Now when that happens, this becomes identity and all these entries have been swept into zeros. Then the lower right hand block is precisely of the form that we want it to be. So you see, the partial dispersion matrix comes out as a byproduct of Gauss-Jordan elimination. This gives us an efficient computational scheme. We have mentioned how the concepts of partial correlation and conditional correlation both evolve from the same idea. The main conceptual difference between them is that in conditional correlation, we remove the effect of z from x and y by conditioning, while in partial correlation, we use linear regression. Thus, some nonlinear contribution of z may still persist in the residuals. That is why typically partial correlation has a different value from the conditional correlation. There is, however, one case where they are the same. If the joint distribution is multivariate normal, then partial correlation is same as conditional correlation theoretically. Unfortunately, we cannot discuss this any further right now, as we have not talked about multivariate normal distributions yet.